Hello, this is the NLP project report for Group 22. First, we'll be going over our methods for question generation, followed by our methods for answer generation. So, to begin with, before we get into the actual pipeline, these are some of the building blocks that we built our system on. Most of these were available as part of the SpaceSeed pipeline, but we used two external dependencies, namely Benopar, which is the Berkeley neural parser for constituency parsing, and NeuroCoRef, which does coreference resolution. In addition to this, we implemented a language model for ranking and scoring our question generation. The first stage of the question generation is article ingestion. For this, we start with the raw text and we sanitize it into a single string. This single string then passes through the NLP pipeline to create two objects. The first object is the regular one, and the second one is the object created after the coreference resolution. We use this to generate 5 different types of questions. The first type of questions are entity questions. Here, we use the named entity recognition and the coreference resolution to detect noun chunks from the SpaceSeed document. Once we have these noun chunks, we filter them for location, GPE, person, and event. We then use these noun chunks to create how would you describe questions, using a slot filler representation. The second type of questions are who-what questions built around entities. For this, we use the constituency parser to parse each of the sentences in the documents and then analyze these sentences to create noun phrase, verb phrase tuples. These noun phrase, verb phrase tuples are then separated into two sets, those in which the noun phrases contain entities corresponding to the word who, and those which contain entities corresponding to the word what. This allows us to create who-what questions that are grammatically correct. The last 3 types of questions that we've generated are all true or false questions. The first are generic true questions, where we look at all the sentences and pass them through a filter which checks for lengths between 10 and 35 words. We then further check if this sentence contains within it a coreference, and if it does, we prepend it with a true or false to generate our question. Next, we have false, true, or false questions. For this, we first extract noun phrase, verb phrase tuples similar to those in the entity questions. But then we jumble them together to create false sentences which sound true and also have high similarity with the reference document. So if you were to look at the example, the noun phrase Ramses 3 and the verb phrase was also compelled to fight belong to two different sentences. The last type of false questions are those in which we replace the ordinals in candidate sentences with the ordinal 56th and keep the rest of the sentence the same. Our general idea with the false sentences was to maximize similarity with the reference document and not introduce any foreign content. This now brings us to answer generation, where we used most of the same building blocks. However, we didn't need the language model to rank and sort, but we additionally did need sentiment analysis and the vector space model. The article ingestion pipeline for answers remains the same. We did, however, experiment with reducing all text to their respective lemmas in an effort to increase similar sentence accuracy, but found that it did not have an effect. This brings us to the question classification pipeline, where we classify each incoming question as an entity question, a yes or no question, or a description question. To do this, we first pass it through the NLP pipeline, and then we check the parse tree to see if the root is SPARQ. If it is, it becomes an entity question. Otherwise, we see if the root is SQ, which would point to a yes or no question, and otherwise we check for true or false, which would also be yes or no, otherwise a description question. We also implement a question classification backoff so that any question that we don't know of, or if we can't find an answer, defaults to a description question. The first and easiest answers we generate are for description answers, which are entire sentences which are the most similar to the text in the query. The query differs between backoff and non-backoff. In the case of backoff, we throw away the question part, such as who or what, and operate on the text alone, and if it's not backoff, then we operate on the entire text. The type 1 entity answers are slightly more complex. First, we pass the question through a parse tree analysis which separates the question word and the SQ subtree. The SQ subtree is then matched against the document to find the most similar sentence. After this, we pass through a series of tests to see if the question word is how, if the length of the question is less than 5, or if the most similar sentence has a similarity value of less than 0.9. In all of these cases, we back off to the description answer for a longer sentence answer. Otherwise, we then isolate the verb phrases in our most similar sentence and find the verb phrase which is most similar to the question. We then walk the parse tree of the sentence to find the noun phrase associated with this verb phrase. This noun phrase then becomes the answer. This provides both conciseness as well as correctness. The last most involved answers are for true or false or yes/no questions. For this, we first take the question and isolate all of the noun phrases in it to obtain the question noun phrases. We also determine the most similar sentence in the document to this question and isolate its noun phrases to obtain sentence noun phrases. All of these units are then combined and passed through 3 tests. The first test checks whether both the question and the sentence match in having not. The second test is, do they both have the same sentiment? The third and final test checks that all parts of the question match all parts of the sentence. This is to guard against Frankenstein sentences such as those generated by R type 4 questions. So we check that each noun phrase in the question has a noun phrase in the sentence which it matches to with a similarity of greater than 0.95. Verb phrases make up most of the sentence itself and thus are handled in the sentence similarity check. And that concludes our video. Thank you for listening.